Well, what we have here is a very nice looking Hitachi V302 30 megahertz dual trace scope. The unit is in immaculate condition. The cabinet is sparkling. It's been repainted, but it's a nice job. And the front panel is clean. There's no scratches. Very nice condition. Knobs are in good condition. And as you're going to see, the unit is in good working condition as well. This unit registers up to 30 megahertz within its bandwidth, which means that you would be able to use it in radio waves all the way through the shortwave area. And probably, I'm going to guess 80% of 90% even of what most people would use a scope for. We're going to give it a test. We're going to show that that the scope is meeting its specs, that it passes in good flying colors on every setting. So it's going to take me some time. Bear with me, but I want to do a good job for you and show you that this is a good unit. It's been calibrated, it's been cleaned, it's been painted, and it's in good shape. So let's go for it. Along with it, we have a manual and a set of probes, so got a whole kit. Hang in there. Okay, what we're looking at the moment is a 30 megahertz waveform. We are running about 0.8 volts peak to peak AC, and we're on channel 1. And we're going to step this thing down. Let's take her down to 20. Alright. This is 20 megahertz. And let's go ahead and take her down now to 10. That would be 10 megahertz. Make it a little easier to see. And then let's go ahead and take her down to 5. There's 5. Two 2.5. 1.25. And take her down to 1. There's 1. Now, let's see if we can verify that this is 1. We right now are on 2 microseconds per centimeter, and we see that we do a complete cycle in 1, 2, 3, 4, 5 centimeters. So 0.2 times 5 is 1. So that would be 1 millisecond, or excuse me, that would be 1 microsecond in 5 divisions. And 1 microsecond, the inverse of that is a megahertz. So you're looking at a megahertz on the screen right now. We see that we are 1, 2, 3, 1, 2, 3, so we're up 6 and down 6. So we are 1.2 volts peak to peak at 1 megahertz. Let's go back to 10. Alright, there's 10 megahertz. And I do 1, 2. Looks like I pulled 2 waveforms in 1 centimeter. And at 0.2 centimeters per division, that means I am 0.1 microsecond wide in my my frequency. So 1 over 0.1 microsecond would be 10 megahertz. So I'm reading 10 megahertz, yes. And I am seeing 1, 2, 3, 1, 2, 3. I am up 3, down 3. That's 1.2 volts over the input there. All right, let's take her up to 20. 20 megahertz. I'm up 3, down 3. 30 megahertz. All right, that would be 30 megahertz. And I am up 2.2 and down 2, so that would be well, approximately 0.8. So 0.8 volts peak to peak at 30 megahertz. So let's mark that down and remember it, and we'll come back and check it. Okay, we've switched to channel 2. We still have 30 megahertz coming in, and what we see the 30 megahertz. Let me see if I can make that as visible as possible on this camera. I don't know. Anyway, we are up about 2.2 and down 2, so we're about the same as we were on channel 1. That would be approximately 0.8 peak to peak, with a little fraction for the 0.2 there. But then we go to 20. All right, we're at 20. And we are seeing that we are right now up 1, 2, 3 and down 1, 2, almost 3. So 6, 6, about 1.2 volts. And I think that would carry on. Here's 10. Up 3, down 3, and then 1. And we see ourselves up 3, down 3, and we have the 1 megahertz trace. So we see that we are 1 cycle in 5 divisions at 0.2 microseconds per division, so that'd be a megahertz. So channel B is matching channel A. We'll go back to A. Okay, we've connected up to this Fluke 343A. All right, we're connected up, and we have a little bit of noise coming in on the line, but that's something we can ignore. Let's go ahead and apply our first step of DC voltage. Let's go 10 millivolts. All right, we're on 5 millivolts per division. We just put a 10 millivolt step in there, so we've risen 2 divisions, as it should be. Let's go in, I'm sorry, let's make it 20 millivolts. 20 millivolts, 5 millivolts per division, we should be up 4 divisions. 1, 2, 3, 4, there we are. Alright, let's go to the next position of the variable volts per division gain switch. And we are right now on 10 millivolts per division, so this is the second lowest or most sensitive setting. We are feeding in right now 20 millivolts, so we are up 2 divisions. That's as it should be. Let's go to 40. And at 40 millivolts, we've maxed out on the screen. Alright, let's go ahead and change our range again. We're now on 20 millivolts per division. We're up 2 divisions. That's 40, up 2 divisions, that's 40 millivolts. And right now we are at 40 on the fluke, so that matches. Let's go ahead and take her up to the top. That would be 80 millivolts. Alright, that would be 80 millivolts, and you see that we're right at the top. That's very good. Alright, let's go 50 millivolts per division. And I'm going to go up a tenth of a volt. Tenth of a volt is 100 millivolts. We are up 2 divisions at 50 millivolts per division, 100 millivolts. Let's go up to 200 millivolts. 200 millivolts, and we are right at the top of the screen. That's as it should be. And let's go ahead and hit the next lowest, or highest. This would be 0.1 millivolts per division. Right now we have 0.2 volts coming in, so we're up 2 divisions. That's good. Let's go 4. And at 4 we find ourselves at the top of the screen. That's what should be. 0.2 millivolts per division. Right now we are up 2 divisions. That would be 0.4 volts, and that's what we were at a moment ago. Let's go to 0.8. Alright, there's 0.8, and we are right at the top of the screen. Again, as it should be. We are at 0.5 volts per division. We're going to go back down to 0 again, and this time we're going to go 1 volt. And with 1 volt, we are up 2 divisions. Because 0.5 volt per division, 2 divisions, 1 volt. Let's go 2 volts. Top of the screen. Again, that's where we should be. Okay. 1 volt per division. We're right now at 2 divisions, that'd be 2 volts. That's where we left off. Let's go 4 volts. And we find ourselves at the top of the screen. Again, where we should be. 2 volts per division. We are right now up 2 divisions, that's 4 volts. And if I go to 8 volts, I find myself at the top of the screen, 8 volts. That's good. And if I go 5 volts per division, and let's go to 10 volts, I'm up 2 divisions. Exactly where I should be. Now at this point, I need to change range on my fluke. But that means I got to back down again. Alright, we're on the 100 volt range. I'm on 5 volts per division. I have 4 divisions up, so maximum I want to do is 20. Let's do 10. I'm up 2 divisions. It's 10 volts. Okay, let's go 20. And at 20, I see I'm at the top of the screen. We went up 4 divisions. Okay, and that's the highest part of the range on this scope. If we were to use the probes with the divide by 10, then this would get us up to 200 volts on this scale. Right now we're reading 20 because we are at 5 volts per division, 4 divisions, 20 volts. If we had a divide by 10 probe, then we'd find ourselves, if we were at full scale, each one of these would be worth 50 volts. So 50, 100, 150, 200. So there we go. Let's go ahead and check out channel 2. We're good on channel 1. And I think what we're going to do is we're going to start on the high end and work our way down. Okay. Alright, we've changed to channel 2. The input is on 2, we're on DC, we're on the highest range. Variable gain is good. Let's check our ground again. Ground is pretty good. Let's just tighten it just a little bit. There we go. That's, for me, that's dead on. Okay. And then we've risen all the way to the top of the screen, so that's 20 volts. Let's take ourselves down to 10. We should be at 2 divisions, and we are. Let's go to... we want to go to 8 volts on the input. We're going to find ourselves at maximum. We have 2 volts per division. We've got 4 divisions. That's 8 volts. If I take myself down to 4 volts, I'm at 4 right now. I'm up 2 divisions. If I go to 1 volt per division, I should be at full scale. And I am. Let's take ourselves to 2. And I'm at mid scale. Mid for the upper half, the upper quadrant. And then if I go to 0.5 volt per division, I'm again at full scale. At 1 volt, I'm at midpoint. If I go to 0.2 volts per division, and I reduce myself to 0.8, I'm at the top of the scale. If I go down to 0.4, I should be mid-scale, and I am. Changing my scale to 0.1 volts per division, I should find myself at full scale once more, and I am. Go down to, that would be 0.2 volts, and we are at mid-scale. If I go 50 millivolts per division, I'm at full scale again. And I can go to half scale by putting in 0.1 volt. 2 divisions, 2 times 50 millivolts is 0.1. That's good. Let's go to 20 millivolts per division. Well, we need to reduce ourselves first of all. Excuse me. Alright. I am at 0.08 volts DC coming in, and I'm going to change to 20 millivolts per division, and I should be at full scale. That's because I have 0.08 volts, so 20 millivolts, that's 0.02 times 4 is 0.08. That's good. Let's go to 0.04. There we are. And I am at mid-scale again. And if I go to 10 millivolts per division, I'm at full scale. And that should put me, I'm at 0.02. 0.02 now, so I'm 2 divisions up, which is perfect. And if I go 5 millivolts per division, my lowest setting, I see that I am 4 divisions up, and I'm at 5 millivolts per division, so that's 20 millivolts, and that's exactly what I have coming in on the fluke, 20 millivolts. Okay. So we checked both channels DC-wise, and we reacted perfectly every step of the vertical division scale. So at this point, let's just kind of look over some of the features of the unit and check some of those. For one thing, we did switch from channel 1 to channel 2. When like right now, channel 1 hasn't got an input, so there's nothing there. Channel 2 has an input, and it's at maximum, so we're at the top of the scale. Okay. I could go dual trace, in which case I see both signals. And if I change my volt per division on the on channel 2, where I'm feeding in a live signal, I'll see it jump, but I'll see the other channel stay steady right now because there's nothing coming in. So you can see that that's dual channel. This is also the XY position, where I can take my sweep and pull it all the way to the right, and I can go XY. And in this case, right now I have a DC signal coming in, so there's nothing happening but of any consequence right now. But I could if this was an AC signal, I would see a Lissajous pattern. We'll check that later. I think my position vertically will change as I change my scale here, and that's what should happen. As my voltage gets greater on the input, you'll see the y-axis react. I'm not feeding anything on the x right now, so I'm not getting a reaction over on the x-axis. But this is how I would get it. We have a each side of the dual trace has the volts per division range switch, and then we have a variable gain switch, which frankly most of the time you won't, I don't see why you would ever need it, but it's there. It allows you to make a signal that isn't hitting a gradical, say a full division. You can adjust it so that it would be hitting a full division, and then you could look to see when you, as you change range or whatever, you see it go to the half step. It's just for your convenience. Both of these right now, they work, but they're both at their maximum position, which is the cow position. We have a XY adjustment, and right now, since we're in the X range, you'll see that we're swinging back and forth in the X position a little bit. And then the Y is that range. Okay. Let's go to what they call additive. In the additive mode, I've taken both the both channel 1 and channel 2 signals, and I've added them together, and it shows me what's there, which essentially right now is it's 20 millivolts. adjust our zero position again, and then put our gain all the way up. Alright, now let's put ourselves back on, and we see that we are one division up, 20 millivolts. So that's good. And then we have the difference. That's a subtractive thing. So let's check our channel 1. Channel 1's not zeroed. There, now it's zeroed. Okay, and let's go subtractive once more. Okay. $20 minus 0 is still 20, so we're good. So let's take a look. We have trace rotation. If you play with this little dial, you adjust the angle that the trace is at. Right now we're perfectly horizontal, so I've already got it adjusted. I'm not going to fool with it. But if I was to turn it, you'd see the whole trace start to skew one way or the other. Focus. Take ourselves from a blur to clarity, and then to a blur again, and then there's clarity right there. Brightness. Plenty of brightness. And we have auto mode for the trigger, and then normal. In the auto mode, you're always tracing, and when you adjust your level until you hit the signal, that'll lock it in. You may not be able to see the signal, you just see a band going across the screen, but when you lock it in, you'll see it stand still. In normal mode, you see nothing until you adjust yourself to lock in on the trigger, and then you see something. That's the difference. Then you've got TV minus and TV positive on here. These are having to do with the frequencies that are seen inside of television sets. If you were adjusting the vertical and horizontal and so on, you would use these frequencies that are built into this thing to see the signal. Most of you aren't going to be doing that, but it's there, and the manual takes you through some of that, so you'll be able to play with it. We have the source of the trigger for channel 1, channel 2, line or external. You can feed an external trigger source in here if you wanted. We can adjust the position of the trace, centering the trace left or right, so we feed across the whole screen. Okay, we're displaying a 10 megahertz signal coming from the 8640B, and we're displaying it at our fastest speed of 0.2 microseconds per division. And difficult maybe for you to see it, but I'll hold this steady. There's very closely 2 cycles in a division. One cycle half, and the other cycle finishes it up. So if I've got 0.2 microseconds per division, then that means I got 2 cycles in 0.2 microseconds, or divide it by half. 1 cycle in 0.1 microseconds, which would mean, since 1 microsecond would mean I had a megahertz coming in, 0.1 must mean I have 10 megahertz coming in. So I do have a 10 megahertz signal, and I do get 2 cycles on here. It's a little more difficult to read, and I did have to switch to this other range. So there is a second way that could be done. I could back off on my horizontal 2 steps. That puts me at a 1 microsecond per division range. Now at this point I have to read 10 of these in one division, and you go, what good is that, right? Well, if I was reading a megahertz and suddenly I saw this, I could reach over and I could pull on the horizontal adjustment knob. I just pull it straight out, and I'll get a magnification factor of times 10. Okay. Now, just a slight adjustment to make sure I get lined up here. Now I see I get one cycle in one division. Well, if I've got one cycle in one division, I'm at 1 microsecond. That would have been a megahertz, but I know I pulled the times 10 knob out, so it must be 10 megahertz. It was much easier to read because I only had one cycle in a division. So the times 10 horizontal is working fine for expansion. There is a limit to its usefulness. If you try to push it up into the upper two ranges, it's not calibrated, they say. So I think you can still use it, but you may find that you change off in frequency. In fact, we could check that. Let's just do that. Okay, so we're back to our 10 megahertz signal, and we're on the 1 microsecond per division. And I know I can pull out my horizontal, and I can get one cycle in one division. Now, if I went to the next step, which is an uncalibrated range for magnified, here's 0.5 microseconds per division. So essentially, it should take me 2 divisions to get that same cycle, that same one cycle at 10 megahertz. So let's take a look, lining myself up with the 0. All right, I see 1. And I'm just slightly less. Not bad. Or 1.95, whatever. Then I would know that in approximately 2 divisions I got one cycle, and I would say I'm approximately 10 megahertz. Well, that's true. And that's the way you would use this if you went into this uncalibrated area. Now let's go up one more. All right, we'll line up my 0 crossing here. Oops. It is a little touchy in the times 10. Okay. So here we go. I've got one full cycle and approximately 4.2 and a fraction, 4.25 divisions. So essentially, I should have received one cycle in 5 divisions. Instead, I got it in 4.25. If I do the math on this, that would be 10. It'd be 1.2 times 10, which would be 12 megacycle signal. So I would have been off by 2 megacycles in this case. I should have stretched out, had that 1 and 5, and I didn't. So being in the uncalibrated range has caused me to lose some of my my expansion as I step up. It still would be usable, and that's why it's here. That's why they have it marked uncalibrated. You're expected to do a lot of rounding. You're just trying to get approximately where you're at. But if you really need to get it dead on, they tell you you're calibrated in the 1 microsecond per division range. So back to that again, and we do see that we are calibrated. So we're functioning fine on the times 10 horizontal expansion. That's really the point. An additional feature that I don't think I went over in my earlier demonstration is that the vertical gain also has a ×5 capability. So if you're in a position where you suddenly see that that you can't really resolve the amplitude of the waveform, and you don't really want to have to change your range. You want to maintain it, but you'd like to suddenly expand an area and just take a look and see what there is. You can pull out on the vertical gain and get an instant ×5 view of the signal that's there. So earlier I was at 1 volt per division, and I had, well, one vision peak to peak could be half a division per peak, and then I pulled my ×5 knob, and what I see is that I have about 2.3 divisions up and down. So if I was 0.5 peak and I went ×5, that would be 2.25, which would be about 2.3. So I did in fact expand my vertical ×5. It's a little tricky to use. You've got to be concerned about your shift in the baseline when you go to use this. It's very easy when you're pulling that knob to make a slight shift, but it's usable. I find it just as easy to go ahead and change the range, but it's an additional feature. So there you have it. You not only get this fine scope, which we've now proven works very well, we also give you this manual, operation manual for the Hitachi. Takes you through all of the functions, what they're for, how you would apply them. Gives you some user calibrations, and then at the back I've included 11 by 17 circuit diagrams for the vertical, horizontal, and power supply systems in the unit. So this is better than what I was able to find in other manuals. So I think you'll find that that's very nice. And then along with that, a nice set of new 40 megahertz probes. These haven't even been out of the pouch yet. I'm taking them out for the first time right now just to show you them. Very nice probes. Brand new. So you'll be all set. You'll have a complete kit, and wish you well in your bidding. Thank you for listening. We'll see you again.